Hello everyone, my name is Kolja Haberland, I'm CTO at LayTec. In this talk I would like to show you our products for in-situ and ex-situ metrology for VCSEL production. At first, LayTec in a nutshell. LayTec is a Berlin-based metrology company founded in 1999 as a spin-off of the Technical University in Berlin. We're having about 70 employees, operating worldwide, and have sold more than 2,500 systems into the field. Our business is to develop and manufacture process-integrated optical metrology, and these systems are used in the semiconductor and thin film industry and academia for applications like lighting, laser, PV, glass coating, and many more. To give you a rough overview about what LayTec is producing, let me show you some of our markets and industry we sell in. Our tools are used for process control in LED production, as well as in laser production. It's used for controlling the function layers on glass, the production of power devices, and in photovoltaics. LayTec's products include in-situ metrology that is used to monitor and control thin film coating during the process in a deposition chamber like ALD, PECVD, or MOCVD. We also provide tools that can be used inline on conveyor-based or roll-to-roll-based production lines to control large area coatings. We also provide mapping systems that are used after the process to spatially characterize the layers for uniformity. And in order to do this, we need to have precise and comprehensive materials databases of the optical constants of all the materials. And we also need to have a large package of software for simulation and analysis of the data. Let me now briefly introduce the value chain in production of a semiconductor device, such as a laser structure. Production starts on substrates that are loaded into an epitaxy system, and at that point our in-situ metrology is characterizing the wafers in the chamber during the growth, and this allows us up to a certain extent to already predict the device performance at the beginning of the value chain. When the wafer is taking out the epitaxy system, the epi wafer can be characterized in the mapping system for uniformity, and later in the production chain, inline metrology in front end and back end is also possible. Let me now show you in more detail how the in-situ metrology works. Here in the center we see the MOCVD system where the layer stack is grown. Wafers are loaded and the layer stack is provided as a recipe. Inside the MOCVD system, our LayTec metrology system is installed on the reactor lid, looking at the wafers during the process and providing a lot of useful data in real time that are interfaced with the growth system so that closed loop control is possible. And the measurement includes wafer and pocket temperature, layer thickness, growth rate, wafer curvature, ternary composition, surface morphology, and much more. And in the end, that is helping you to produce better devices such as lasers. Here's a real-life example of the in-situ fingerprint of a VCSEL or DBR structure growth. We see here the reflectance signal coded in colors, and we can extract the behavior of the reflectance at certain wavelengths over time. And we can also extract spectra taken at a specific time, showing us the whole reflectance in the visual, infrared, and UV range. Analysis can provide growth rate, surface roughness, composition, interface grading, cavity position, and stop-band position, and is very valuable for understanding the growth. After the epitaxy process, the wafers can be characterized ex-situ in a mapping station with white light reflectance and photoluminescence. Inside this box, we see the optical head and the wafer. Wafers are loaded, and the result is a two-dimensional mapping of the reflectance or photoluminescence of the epi wafer, providing, in case of VCSELs, stop band position, stop band width, cavity dip position, cavity depth, cavity dip width, growth rate and layer thickness, and ternary composition. The mapping system combines reflectance and photoluminescence measurement, allows an XY mapping of the complete wafer with one optical head and no realignment for wafer sizes up to 200 millimeters. The spectral detection range is customizable in the wavelength range between 200 and 2000 nanometers, and for the photoluminescence, different lasers are available. It all comes in a package with advanced analysis features. But you only get the full story about your device if you combine the in-situ metrology with the ex-situ mapping. From the in-situ metrology, during the epitaxial growth, you already have a good understanding of what you have been grown, of the real layer thickness, maybe compositions or interface properties. And this knowledge is available at the time when the wafers are loaded after the epi run into the mapping system. So the depth information over process time is already known, and this can be used as additional information for the interpretation and analysis of the uniformity that is measured by the mapping system. Only by combining these two information, a comprehensive three-dimensional growth analysis can be performed, and you are provided with much more valuable data than just by ex-situ mapping or just by in-situ metrology. So it's the combination that makes the metrology real valuable. So I thank you for your attention. Please get in touch if you're interested in learning more. Here are the links to our website, email contact, and the link to our LinkedIn profile. Thanks again for your attention.